So I want you guys to try this one. I list the equation here. You can use this equation. I'll show you how to calculate the mean value, and I'll ask you guys to calculate the uncertainty of the extinction coefficient. Putting Beer's law, the absorbance equal to the extinction coefficient times the length of light path, that's L, times the concentration, right? So I can get the extinction coefficient equal to A divided by L times C. And I can calculate, use the measurement values. So A equal to this one, and the light path L equal to 1.0, and the concentration equal to 13.7. So I can get the extinction values. Now I want you guys to work on the associated uncertainty. Let's see. So first term, I take the partial differential of A. I should get this, right? That's pretty straightforward. And the second term, I should get that. This third term, and even though there is a minus sign in front, but eventually we're going to take a square, so that minus sign doesn't matter. So we can plug in all these values. So that's what I got. Eventually for this one, I'm going to report the final result as epsilon equal to 0.013 liter per centimeter per mole plus minus 0.001. You don't remember some of the partial differential. I put some useful uncertainty equations here. If you see this form of function, you can find this corresponding uncertainty calculation quickly. Let's consider an even more complicated example. Say I have a function z that it has two variables with m and b, and the m is slope from the linear plot. So if I run a linear plot of the measurement data, I can get m as a slope, and a b, that's my intercept. So m is slope, b is intercept. And this function z equal to 2 times m times the square root of b. Here, I have some uncertainty in m and the uncertainty in b. That's what we found in the Excel regression analysis. Remember, in the toolpack, I can look for the value of m and b, as well as the uncertainty in m and b, right? I have this data, and we run the uncertainty, and I can find m equal to 0.457 plus minus 0.008, and the b equal to this value. And now we go back to look at z equal to 2m times the square root of b. And what's the value for z? And it's uncertainty. Right, the value for z is easy to calculate. Now I want you guys to calculate both the z and the uncertainty of z. So with this function, we use the equation just as before. And here, if we take the partial differential of m, there'll be 2 times the square root of b, right? Partial differential from m. And if we take the partial differential of b, so remember the power of b in this case is 0.5, half, right? When we take the partial differential, the power of b becomes 0.5 minus 1. There'll be minus 0.5, so there'll be m divided by square root of b. And we can substitute these into the error formula. look at the square root of the sum, and what I got for the error is 0.0257. And by looking at the M and B value plugging here, I got Z equal to 1.32. And then I round this up according to the significant in here. And I got the final answer will be 1.32 plus minus 0.03. So in this measurement, I got one Z value, but in order to get one Z value, I measure multiple data points, right? I measure this data point and get the linear relationship and get the slope and intercept, then I can calculate Z. So is this Z value from single measurement or multiple measurement? It's a single measurement. So you are looking at the representation of a single measurement here because we only have one Z value. However, if we repeat the graphical analysis 5 times meaning we take multiple measurement of the same X and Y, we measure them multiple times, 5 times. And we generate 5 different linear lines, and that give us 5 different M and B's. So we can calculate 5 different Z values. How would we report the Z and its uncertainty? You don't need to do the propagation calculation one more time or 5 times, right? You just get the 5 Z values, and then now you can do the average. When you get to the average, remember to look up the T table and use the degree of freedom, and then calculate the lambda, then you can report Z plus minus delta Z. So what if there is one of the 5 values of Z seems off? So one of the value probably too high. What would you do in that case? So just do a Q-test and see if the value can be dropped before averaging. So that's before you report the final delta Z. Once you drop that Z value, that particular one, then you report your mean with the other 4 Z's, and also look up the T table. Now use n equal to 4. So the degree of freedom will be 3. So to summarize, today we reviewed the systematic error and the random error. And if there is a systematic error for a particular data point, we can use the Q-test to eliminate one data point. Remember, that's only one data point. If you have a multiple data point that seem to be outlier, you shouldn't use the Q-test. Random error, we assume that's all normal distribution. When the number of events is limited, we use a T-table to estimate the error. We also review how to calculate the propagation of errors when there are multiple variables involved. We also see an example of the standard error in the regression analysis. When there is only one measurement in regression analysis, how do we do the standard error? And when there are multiple regression analysis, how do we calculate the error?